Thanks, Andy.
Speaking like Yoda.
It's a real pleasure to be here. I should say right off the bat that this work was done primarily by my graduate student, Shangyao Yu, who's a fifth-year PhD student at MIT. And he made the slides, but all errors are mine, and anything that you don't understand is my fault. So I'd like to tell you about some work that we're doing that is really computer architecture based. At least we started out being a computer architecture group in the context of this project, and worked on a problem of cache coherence, which is an important problem to build shared memory computers. But it's kind of taken on a life of its own, and so that's why you see software in the title. And we've taken these ideas and applied them to databases, concurrency control, and we have some I guess, grand plans going forward. So hopefully you'll be, I don't know, a tenth as excited as I am about this work once I'm done. Just a minute of context. I think you folks all know this. Moore's law is been with us for half a century. We think of it as the printing press for the currency of performance. It allows software designers or developers to write less and less efficient software, but have it run faster and faster as generations of Moore's law keep going. But the fact of the matter is that we have some issues here with respect to Moore's law. And a lot of people outside of probably this audience conflate Moore's law with Dennard scaling, which is something that I just want to point out. Dennard scaling was exemplified by the frequency of processors, single processors, increasing at a significant rate. And Dennard scaling, as you can see here, stopped around 2005. But Moore's law did not. And Moore's law is, of course, the doubling of transistors every generation. And in order to actually get performance, architects had to exploit parallelism. So as you can see here, clock frequency stopped increasing, the flattening over there, and so the number of cores on a chip started increasing. And so you can get commercial products that have 50, 60, close to 100 cores on them. And as Andy mentioned during the introduction, there's an issue now associated with trying to get speed ups from these parallel cores, because while the sequential algorithm didn't really care about coordination or sharing of variables, the parallel decomposition of a sequential algorithm has to obey sequential semantics, or whatever semantics that you would like it to obey, and synchronization and coordination becomes very difficult. And so it's been a challenge to get the linear speedups that you'd like to get as you've gone from 1 core to 4 cores to 8 cores and so on. I want to say a little bit about the different kinds of parallelism that there are in the world today. As a computer architect, this is the kind of parallelism that is closest to my field, to my psyche, if you will, where you have a few instructions, and there's a sequential semantics associated with these instructions, that the value of D that you see here in the third instruction should be computed by the second one. And so there's a dependence associated with these two values that you have to obey. And in a sequential program, it's sort of automatically obeyed. But if you try to exploit instruction level parallelism and try to run these instructions across different cores, or perhaps even in different functional units on a given core, there's waiting possibly that needs to happen in order for the correct value of D, the new value, to be used in the computation of G. Right? So that's an issue. Oh, I should mention, by the way, that I'm perfectly happy to answer questions during the talk. So if you just raise your hand, I'll stop. Go ahead.
Why only linear speedup? I mean, there's this thing called a grand challenge list. We need better than linear speedup.
Do you mean, well, I don't know how to give you that. I should say that. In the context of this talk, I want to essentially give you a solution where you could pretend that the sequential processor ran 5 times faster Okay, so which would be exactly linear speedup, right? I think if you're allowed to change the algorithm and you're allowed to change perhaps the correctness criteria of the algorithm or the results that you want, you could certainly go there. But the semantics that I'm focused on in this talk really corresponds to, as you'll see as I go along here, mimicking these computations. Right? So it's a bit of, it's more narrowly focused than the grand challenge. Right? There's another class of parallelism that is also going to be important for this talk, which comes from the field of databases. And in the field of databases, you have transactions. Transactions are usually fairly small sets of reads and writes and perhaps computations, which aren't really shown here. And there's parallelism associated with these transactions, but you do have a constraint. Just like you had a constraint about the value of D in the first example, you do have a constraint with these transactions in the sense that you have to ensure that these transactions are atomic. And I'll say a little bit more about that, but you can assume for now, from a parallelism standpoint, that each of these squares that you see here, these red squares, could be run in arbitrary order, right? But you can't split them. I mean, these red squares have to be atomic. You can't insert one into the other. And as I said, I'll say a little bit more about that. So those are two classes of parallelism. Let's go on and look at higher levels. You could imagine in a multi-core processor that you have thread-level parallelism, where you have different threads running on different cores. And if you were multiplying two matrices and you wanted to get parallelism, then you might do a row column multiplication to write one particular element of this product matrix C. And you could run essentially n square if you had an n by n matrix threads in parallel if you had enough cores. And this would work out pretty well in this particular example. But that's thread level parallelism. There's many operations that are being performed. In this particular case, in this particular algorithm, there's little dependency in the computation of the result. Even though you have shared data, it's only being read. The two matrices A and B are only being read. Task level parallelism would be you want to search for an image on Google or your favorite search engine, and there's a lot of data being scanned. That could be done in parallel. There's going to be some sorting that happens at the end of the data collection, which has to be a little bit serial. There's some dependency there, but there's a lot of parallelism here. And then there's user level parallelism, where if all of us were searching for different images on Google, the data center associated with the particular searches that we're conducting has to essentially service all of our requests, and there's a lot of parallelism there. User level parallelism in my group is called embarrassing parallelism, because there's just so much that you don't have to work very hard to exploit it. I want to talk now about dependency, because this is fairly fundamental to this talk. And as you can imagine, dependency destroys parallelism. And if I tell you that you have to compute this particular array, and if you notice, I've made it particularly difficult, so my compiler friends would be annoyed with me by having this indirect addressing corresponding to the array, where I have A of bi, and B of I is essentially this random mapping that you don't really have control over. And you notice that A of bi depends on A of bi minus 1. So there's this chain of dependencies, and it's really pretty hard to parallelize this. You could flatten it out, but then if you don't even know what n is, because it's a dynamically assigned variable, that would be difficult to do. And so this is painful. Right? So dependency destroys parallelism. You essentially have a situation where you'd like to avoid dependency. And so let me talk a little bit about different kinds of dependency, just like I talked about different kinds of parallelism. And there are basically 4 different kinds, if you think about it from a standpoint of reading and writing variables. And you can imagine what they are. You have reads and writes, and you combine them in different ways. If you have 2 reads, there's really no dependency. So I guess there's maybe only 3 kinds of dependency. If you have 2 writes, then it's actually something that bears some thought, because you're going to get a value at the end of these 2 writes. And if you don't care about what this value is, I might be writing 14 followed by 15, and it's okay from a program correctness standpoint as to the final result being 14 or 15, then there's no dependency here. right? Now, it turns out this is kind of a little bit strange here because usually you just don't write. Usually you do an update, which includes a read followed by a write. So in that sense, you have reads and writes being mixed up, and they're not these particular simple examples. But if you just look at write after write dependencies, semantics decide order. If your semantics are flexible, you can ignore them, right? And for the purposes of this talk, we're just going to ignore that. Yeah, go ahead.
But it might be that writing A is not an atomic operation.
Oh, absolutely correct. Yeah, no, a great point. I should have said that as a computer architect, I kind of assumed that when I was reading or writing a particular memory location, and you're absolutely right, it was a single instruction, and single instructions were atomic. So you have to take that into account to, I guess, really understand my statement. And so thanks for the question. Right, so you're absolutely correct that if the write was split up, then you have problems, and you're kind of in the transaction world, okay? Because you want atomicity. So the most interesting kind of dependencies are raw and war dependencies, and as their names indicate, you have read after write, where the read needs the new value, and that's really the kind of dependency that I've talked about in the instruction level parallelism example and in the loop example, right? So these are hard. If you need the new value, you need the new value. You got to wait for somebody to write it, right? And another kind of dependency that is being obeyed in exactly the same way that the raw dependency is being obeyed in prior work for the most part with little or no flexibility is the war dependency, where you want a read to happen before the value is updated, right? So there's, and I should say, by the way, that the reason these are skewed out here is that these are two different reads, potentially in two different threads or two different streams of computation, and they could be running in parallel on two different cores. Right? So those two reads could happen in parallel, and we're really saying that those two writes, it doesn't really matter whether they happen in parallel or not, but these two have to have a dependence. So while they may be running on different cores, you got this ordering to worry about, and then the same thing for the war dependency. But it turns out we have a lot of flexibility here, and really for the rest of this talk, I'm going to be telling you how we're going to kind of basically throw away war dependencies, right? And that's going to help us avoid dependency and run our programs faster, right? So that's really the focus. One last thing that I have to talk about is relate all of this to the notion of time. We've really talked about dependence, and implicitly in all of our conversations, and certainly what I've talked about here, we've talked about physical time. When I say after, it means in physical time, right? But there's no reason why time has to be physical. I mean, we are talking about software programs and the virtual world, and so time could be logical. And some of you folks may have heard of Lamport clocks. There's some relationship between that and logical timestamps that we use. Not exactly the same, but the bottom line is that I could just decide that my kind host there is number one in my book, at least for today, and he's got logical timestamp number one, and this gentleman here has Gage has timestamp number two, and I'm at 3 here, and we've just decided on an order that's associated with operations. The interesting thing is that it's not clear, and I will show you that there's many cases where there's no reason why Subhashish has to go first, even though he had logical time 1. In physical time, Subhashish could be last, right? And I could be first, okay? So there's a difference, and I'm going to hopefully convince you that this difference is important and that we can exploit this difference to make programs run faster. So time is really a definition of ordering, right? And so there's some global order and some correctness criterion that has to be satisfied, but the actual operations could be run in different physical times, right? And in fact, if you were time zones, and obviously we have different notions of time on the East Coast and the West Coast, and we think of them as ordered simply because we know it's -3, etc., but we didn't really have to. We don't really have to. So let me give you a concrete example, a really simple example of how we can do this flipping that I just mentioned to you. And we'll look at the war dependence because that's kind of the one that we're after. And in the case of the war dependence, I have 2 threads here that correspond to a read and a write. And the war dependence says that that the write after read. So we want the write to happen after the read. But there's nothing that's stopping us in current computers to do the write before the read in physical time, as long as, and make the copy, make that value 13, as long as there's a local copy of A in the local processor, and that's at 10, and that reads 10, right? So really dirt simple example of how you don't have to obey physical time constraints while obeying logical time constraints and having program semantics being correct, right? So keep this in mind. It's going to get a little bit more complicated, but this is the essence of the avoidance of dependency. So physical time, different from logical time. So what is correctness? I mean, I keep talking about correctness, and I haven't really defined it. Well, you need to have a precise definition of correctness if you want to compare a parallel execution with a sequential execution. In the precise sense, you want some sort of ordering definition or a definition with respect to what the results are going to be in order to say this parallel execution was correct and this one was not correct, okay? And so there's been many definitions, and typically there's a relationship between the outputs or the ordering, like I said, from the parallel to the sequential. And so one of the hardest notions to obey, which is kind of the most stringent notion that, that computer architects deal with and build parallel processors for, is the notion of sequential consistency. And while our work applies to weaker consistency models, since this is kind of the highest bar, it makes sense for me to focus on it. And so sequential consistency says that I have two threads, and they have A and B, and it's specified that A comes before B. Same thing for the second thread here for C and D. And I want to have a global memory order, and you can think of A and B as being reads and writes, and you can kind of ignore the additions and the subtractions and the computation, because it's really all about the memory. Because that's where the values reside, and that's what you're going to look at the end of it. And so these orders that I show you here, AB followed by CD, namely running the first thread followed by the second thread, or the other way around, that's fine. And you can also interleave, so you kind of have this and you have this, and you can do this, you can do that, you can do this, but you can't do this, right? You can't invert A and B or C and D, and you've inverted A and B here, so that's incorrect, okay? One other thing you have to keep in mind is that if you chose this particular order, then if B was a read and C was a write, B absolutely has to get the value that was written by C, okay, in the parallel program, right? And if you don't do that, then you're not going to get the correct outputs, right? So that's essentially the two parts of this, right? You can't reorder inside of a sequential thread, and once you've decided the order, you better be obeying the dependencies. But interestingly, the dependencies are different. The dependencies are different corresponding to these different executions. And that's it in terms of, if you want a 10-second spiel for my talk, it's this, which is we're going to exploit the degree of freedom associated with the execution corresponding to the correct sequentially consistent executions in order to find the one that requires the least weighting, has the least dependence, and runs the fastest. Okay, we don't guarantee optimality or anything like that, but we absolutely guarantee correctness. Okay, and we're going to use these ideas in a couple of different contexts. But the first thing we're going to do is exploit this in the context of cache coherence, which is essentially a difficult problem that corresponds to ensuring that you have shared memory on a multi-core machine. Right, and it gets more difficult as the number of cores increases. So in the rest of the talk, I'm going to essentially do three things. I'm going to tell you about how we can solve cache coherence better under some metric using this idea. I'm going to show you how you can solve concurrency control in database systems better, again, in some metric using this idea. And that's work done in collaboration with Andy Pavlo, who's a professor at CMU, and Daniel Sanchez, one of my colleagues, a Stanford alum. And then I'll give you a sense of how things change at the atomic synchronization level in terms of load reserve, store conditional, and those basic instructions at the processor level that give you synchronization, and what our plans are in terms of taking this in and building it into systems, software systems. So multi-core processors and concurrency control are really the meat of this talk. So let me talk a little bit and give you some context on why we'd like to improve shared memory and the efficiency of shared memory. So the canonical way, at least right now, of implementing shared memory is to use what's called directory-based coherence. And directory-based coherence corresponds to, if you, let's say you had 9 processors here, and they each have caches. So the P's are processors, and they each have caches. And you have different colors here associated with data. So each color represents the same data, same cache block. And you can see that this pink data is in a few different places. And you want that to be local to you because locality is great from a performance standpoint. And if you want to go further away, then it takes longer. So it makes perfect sense to replicate data if you can keep it close to you, because you can't build large, giant caches that you can access very easily. They take up too much power. They use up too much area in terms of the number of ports. But what you can do is, of course, replicate and cache locally. But then there's a little bit of a problem. The problem is that there's coordination that may be required, and you're trying to run a sequential program, and you're trying to parallelize it and run it obeying the sequential semantics. And so if you ever write to it, then that write is going to have to invalidate all of the copies, because there's many copies. You don't want to have incoherence in the system where you have the same variable, if you will, being 12, 13, 14, and 15 at the same time, at the same physical time. That's important in the system. Okay, and if you didn't do this, which was when this middle processor wants to write the pink data, if you did not invalidate all of the other copies of the data and then wait for acknowledgments, then take it from me that you would violate sequential consistency. Okay, that fact is in textbooks, so I won't say more. Including Patterson and Hennessy. Since I'm here, I should mention that. But the pain involved here is associated with the broadcast of all of these invalidation signals and the collection of these acknowledgments, and this pain increases as the number of cores increases. Not only that, you also have to remember, unless you're willing to broadcast to all 100 cores in the system and wait for I don't have it, or yes, I had it and I invalidated from all 100 cores, you do have to take into account the bookkeeping cost associated with remembering which processor had which copy of data. And that's essentially a directory structure that's kind of annoying to keep track of and to store, because this is in hardware. So if, in fact, you went from 64 cores, where it's not a big problem, and so I won't belabor the point, in terms of the overhead involved in this bookkeeping information, and if you went to 1,000 cores, you're talking about a 300% overhead in terms of the bookkeeping versus useful data, which is completely ridiculous, right? So you don't really want to do that. So we'd like to avoid this, and one way you could avoid it is to use this notion of leases, which is basically a library scheme. Okay, and so this is nothing to do with our logical timestamps yet, but I'm going to relate this to logical timestamps in just a minute. But let me just talk about lease-based coherence and libraries. So you can imagine that in order to avoid the bookkeeping cost, I give data that is valid for a certain amount of time. We'll call it a lease for a couple of time units, whatever that is, to a particular processor, core 0. And that processor, during that time, can keep loading the data. And then after it expires, then you actually have to renew the data. So the data expires, it's invalid in the cache, you have to go get a new copy, and you have to bring it back, right? So you have to choose this lease properly. In a lease-based coherence model, if someone has a copy and someone else wants to write it, what you end up having to do is you have to wait, as this dotted line shows, for that data to expire. And that waiting is going to be a function of the length of the lease. So it becomes incredibly important to get the leases kind of exactly right, because the leases are too short, you keep renewing, And if the leases are too long, then you wait on writes. Okay? So this doesn't actually work. And I've tried very hard a few years ago to get this to work, and then I couldn't get it to work. What we do in the Tardis protocol is use logical leases. But before I tell you about Tardis, let me tell you the one nice thing about this lease-based protocol. The one nice thing about this lease-based protocol that you might have guessed is that my bookkeeping information is much less, because I don't need to know who checked out this book from the library, right? All of you could have checked out this book if you're processors or a subset of you. What I need to know is the maximum time associated with all of your leases is just one number. And that maximum time, sadly, is the time that I have to wait for in order for someone to write the data, right? So I've gone from order n bookkeeping information to order 1 bookkeeping information, but what I've done is created another problem that's associated with the write latency, okay? But there was no invalidations and there were no acknowledgements and there was no order n information, right? So that's why I was pumped up about this idea a few years ago, but I couldn't get it to work because it's very hard to choose the leases correctly, and as I mentioned, I won't repeat myself. So the cool thing here is that using the notion of logical time, we're going to fix this problem. And we're going to, that's where the title, time travel, what have you, comes in. We're going to actually fix this problem. And so we're going to be back to not physical time leases, but logical leases. And so we're going to have a program timestamp associated with each thread, the loads and stores corresponding to each thread. And so there's like multiple clocks associated with each different processor, which are keeping different times. So this is, and they may vary, they may get closer together, and they may jump ahead, etc. You never roll back, but you could jump ahead, so the rates of incrementing these clocks are different. And so we're going to basically have 2 timestamps. The 2 timestamps are, and this is important because this is incredibly important because every algorithm that I'm going to talk about from here on out is dependent on the definition of these 2 timestamps. And the first timestamp is the write timestamp, or WTS as it's shown here, and the second one is the read timestamp. The write timestamp, you can think of it as the version of the data. Every time I write the data, I'm going to increment the write timestamp at least by 1, because I need a new version of the data, right? So if I see 2 pieces of data with 2 different write timestamps, whether the values are the same or not, I know that there are 2 different versions of the data. And RTS is the read timestamp, and the semantics there are simply that the data is valid when it was written, which obviously was when the write timestamp time started, till the read timestamp value, right? So that's the lease, right? So it's between WTS and RTS. And so, yeah, go ahead.
Where are these kept?
So I'm definitely going to answer that question, but in due course. Okay. Yeah. What we're going to do is replace this invalidation. And you kind of get the sense of that because we already replaced it with the lease idea. But of course, that was done in physical time. We are going to use this lease idea, like I just showed you, with the WTS and the RTS. But we're going to do these leases in logical time, which, as I mentioned, is a concept borrowed from multi-version databases or multi-versioning in databases. And so that's essentially the picture. So I'm going to answer your question, and I'm going to show you an execution of the Tardis protocol on an example. And it's a simple example, but it highlights, I think, the interesting feature of this protocol. And I'm happy to answer questions along the way, but probably best after, well, you can ask me questions anytime through the animation as well. I want to say that the animation I'm going to show you is in physical time, okay? But what actually is happening in terms of dependencies is not necessarily in physical time, right? And I'll get back to that. So what I have here is simply the setup, and I have a core which has a PTS, which is the program timestamp. Think of it as a timestamp of the thread that is running, not necessarily the processor timestamp. P is for program, not processor. And my cache line is going to, in the highest level of cache, is going to have well, I'm not showing the value here, but this is essentially saying that it's a shared value or it's a modified value, so there's a couple of bits there. And then it's going to have a WTS and an RTS, which is 0 and 10 in this case, right? And so, and then I'm just assuming in this simple example that each core has a L1, one local cache, and then there's a shared last level cache, you can call it L2, that corresponds to the memory, right? And so there's only one copy of A could be replicated across multiple cores in local caches, but there's only one copy of A, if that, in the shared LLC. There's at most one valid copy in the LLC. So that's pretty much it. And so this is the description. One last thing here is that I want to emphasize that the lease is between WTS and RTS. And let's dive into this two-core example. So that's our setup. I'm going to start with 0, 0. This is the cache. It's empty. That's what I got here. All timestamp values are 0. I don't really care about the values of the data itself. I mean, they're kind of irrelevant because we're just doing reads and writes, and the semantics has to be correct regardless of the values. We're going to run this particular program, and the animation, as I mentioned, is going to run in physical time, and it's going to be ordered like you see here, 1, 2, 3, 4, 5, right? So let's dive right in. So core 0 is going to do it wants to do the instruction 1, which is a store. So what it does is it goes over and says, I need to store, I don't have it in my cache, and I want to store A, so I'm going to go ahead and do that store. So I do a request to the core, and it now says, I'm going to give it to you. You're going to modify this because you asked for a store, and the S became M in the cache. And now I've created a new version of the data, and this data was given to me if I'm core 0, being an owner of the data, and so the WTS and RTS are 1. Because it's modified, I'm going to be able to do anything I want to this data. It's kind of my private data at this moment in time because there's only one core that's interested in it, right? But I did have to increment that WTS because I created a new version of the data from the initial version, right? So now I want to do a load B, and load B goes over here, and then it's just a read. So I'm going to now ask kind of arbitrarily for a lease of 10. And so that was completely arbitrary. Because my PTS is at 1, it got incremented. When I wrote this, I have to increment that PTS. I'm going to get essentially this data back. So I want to do this load. And when I did this load, I asked for a load. This is the same processor, core 0. Its PTS got incremented to 1. I arbitrarily chose the lease to be 10. And so now I'm going to get essentially B, which is shared. And I didn't write it, so the WTS is still 0. And it's going to be valid till 11 because that's 10 after my PTS. Okay? So that's essentially what we have here. All right. Now things get interesting. So far, nothing much happened. I want to do a store of B, which clearly is stored in core 0 now, but I want to do the store in core 1. Okay, and now I do a store request. What this timestamp manager tells me is that the B is actually in shared form in a different core. And in particular, the timestamp manager knows that and there may be multiple cores here, the timestamp manager does know this number 11, as you can see. And if there were multiple cores, it would be the max of those values, right? But that's not particularly important, but good to know. So in a lease-based scheme that was based on physical time, I have to go TicToc, 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 let's say 10 times in order to get to the point where I can write this. But since this is the logical scheme, I just decide that I'm going to get exclusive ownership of a new version of the data. There's no invalidation. I'm just going to send back this cache line in exclusive form, and this core is going to jump ahead in time and change the value to whatever it wanted, but set its time to be 12 and create the WTS to be 12. And in this case, it owns the data, so same as the first example, the RTS would be 12 as well, right? So what you see here is incoherence from a physical time standpoint. but it's completely okay because it's two disjoint worlds that aren't really intersecting in terms of time. Okay, these versions are going to be ordered in logical time. So the rest of this is not particularly interesting, but worth going through just to see what happens in a couple of more instructions. It's not that long. So let's say core 1 wants to do a load, and now load is A, and this value was changed in core 0. So what this entails is a request for a load. You do what's called a write back, because this the timestamp manager knows that the owner of this data is this particular data is core 0. So core 0 now returns this data, and notice that the lease is now something that is going to take the RTS and turn it to 22. And you might say, why 22? And the answer is the PTS here, our lease is always 10. That's our default value. The PTS here was 12. And so you want this data to be stored in your local cache for 10 time units corresponding to you. So, and you may as well update it over here as well, because the maximum value that you get, it's fine for this to be 22, this to be 22, that to be 22. I mean, you could leave this as whatever it was before, but the fact of the matter is that any operation that writes A is going to have to jump to 23 now. So it doesn't really matter. So this is a small optimization, which if you didn't quite get, it doesn't really matter. And then finally, a load here corresponds to just reading that value. Nothing really changes. Notice, though, that on reads, the timestamp counter doesn't have to increment. Okay, so this actually is going to pose a little bit of a problem that I'll get to a little bit later. But we do not increment on reads, and that's actually the difference between logical timestamps in our protocol and Lamport clocks, which increment on every operation. Right? And we also jump ahead in time, so that's a little bit different. Right? So what exactly happened here? I clearly didn't do any waiting. It was just back and forth, right? There was no latency associated with waiting for something to happen. There were obviously a bunch of operations. And then there was no broadcast, even though there were obviously only 2 cores here. But even though you had lots of shared copies, it was always kind of a point-to-point communication. All right? Those two are important to know. So what happened? Oh, so this the thing that's interesting here, if you look at what's happening, all of the operations here are happening at PTS equals 1. And all of the operations here are essentially happening at PTS equals 12. So if you really think about this, while the animation showed you the physical time, in effect, because we are going to do a logical time order, the operations in core 0 all happened before the operations in core 1, right, in logical time order. Right? And so the picture here is the following. What you see here is the physical time order, but actually what happened in terms of the program semantics was what you see on the right. Because this all happened at logical time 0, and that is in fact correct. The load B is in terms of the value that this load is getting. I'm sorry, this load and that load are getting are the same, right? It's not that these values are different. Go ahead, Subhashish.
I thought, on the previous example, if you
Yeah.
go back to the previous slide,
Sure.
I thought you were going to make the point that from a performance standpoint, the benefit that you would get is that if that second code, after storing the B, if it was trying to load the value of B or something like that, somehow when it is owning that particular stamp, then you don't have to wait, and that
absolutely.
that would be your, because otherwise
No.
if some other core had to load the value of B, you still have to do invalidation and all that basically, or if some other core had to store the value, you have to do invalidation and all that anyway, right?
Right. So what you said actually also happens in this particular store. So in this store B here, because this load happened, I did not have to invalidate this copy as well, right? And so let's assume that all of this core 0 was replicated in 20 different cores, -1 through whatever, and each of those had loaded the B values. In a directory protocol, you would end up having to send all of those things, right? So thanks for bringing that up. So that's important. I did not wait, and I jumped ahead in order to get a new version of the data. For the purposes of making this fit on a slide, we stuck with 2 cores. So this is kind of the contrast, right? So that's kind of the important thing here. It is important to understand that it's not that this is purely logical time. There is a physical time order associated with these operations. They happened in program order. So if you take a look at the dependencies, then basically what's happened is the original execution, if you executed it and you assumed that you were using a directory protocol, you would have all these dependencies that are shown here. On the right-hand side, there's only one dependency that we have to worry about, which is the red dependency corresponding to the raw dependency, and that simply says that the load A should get the value corresponding to the store A over here, and that's actually what happens because of the write back. The war dependency, I've just shown it in green because it doesn't require any weighting. It was a dependency of convenience. That's the way we think about it. We decided that we wanted to write this value, and in fact, this value is going to get written instantaneously, and it's not really a war dependency because you've created two versions of the data. And so the actual, in terms of being a little bit precise, the actual notion of time here is a combination of physical time and logical time. And in particular, you can see that all the 1s happen before the 12s, but notice that the 1s have to be, we have to do a tie break on the 1s, and we have to do a tie break on the 12s because it's not unique. Timestamps are not unique. That's the only subtlety that I want to point out. So if you want a precise definition of physiological time, which we call physiological time for ease of pronunciation, it's just physi-logical, is that if the logical timestamp of x is less than y, then sure, in physiological time it's less, but if they're equal, then you have to break the tie using physical time, which is essentially program order. All right. So what does this all mean? Did I answer your question about where the timestamps are stored? Right. Yeah. Good.
What's the unit?
The unit is well, it's 16 bits, and you just increment.
No, I mean,
yeah.
it's per cache line, per word.
Oh, sorry, cache line.
Cache line.
Yeah,
Okay.
cache line.
So false sharing would be a problem.
Absolutely, right. I mean, that part doesn't go away, right? So there's a lot of details. There's a lot of bookkeeping, but there's a longish proof, which is not very complicated, that says that this protocol will produce a global order under this definition that obeys sequential consistency. Right? Yeah.
And what about the memory model? Because we don't have sequentially consistent memories.
Right. So it turns out you have to do a little bit more if you want to build this on an x86 machine, and you'd have to do a total store order. And it turns out the protocol we do have a protocol for it, but it requires a little bit more work. Right? And I'm happy to talk to you about that offline. Right? So let's talk a little bit about pros and cons. I'm not a big person in terms of quantifying work in terms of numbers personally, but obviously to publish papers we need a lot of numbers in this community. But I'll point you to papers. But I just want to talk at the qualitative level as to why this would be interesting to a computer architect. And let me say right off the bat that I don't think it's interesting for small scale systems. If you really need to get up to 100, 200 cores, this would be interesting. Because this is scalable. It's scalable in terms of the bookkeeping cost, and it's scalable because it doesn't require any invalidation or multicast or broadcast. There's a problem with lease renew, and it turns out, I mentioned the logical lease problem where you could essentially, you had to decide what the leases were. It's much less of a problem here. We arbitrarily choose a lease of 10 because we don't have to wait for leases to expire. And number one, when you renew leases, we speculate that the leases will be renewed and hide the bandwidth of the data coming back by essentially saying, just tell me if I could renew the data and renew the lease, which is much smaller amount of data. And on top of that, we speculate to hide the latency. So you can have an out-of-order speculative processor or an in-order speculative processor that would hide the renewal latency. And that's what we do in our experiments through speculative reads. Timestamp size is an issue. It turns out we can do some timestamp compression and get it to be a small fraction of the cache line size. And there's a little bit of a problem of reads not incrementing the timestamp. So if you ever saw a Doctor Who episode on time standing still, this is not quite a not quite a research realization of that, but there is an issue if you have spinning and you use spinning to check on a value of a variable, you would never get out of the loop. And so you do have to increment the time periodically at some rate in order to avoid the live lock that's associated with this. Right? So that's kind of the summary of Tardis. Right? I think we are at the point where I'm done with this. I can certainly take off. Yeah, questions. Yeah.
What happens if you have multiple cache levels? You talked about.
The question is, are those cache levels private or shared? Are they sharded or private? It's not a big deal. There's timestamps that are required for the different levels. What we think about the timestamps as being determined simply by the L1 cache or requested by the L1 cache, and those values would percolate through let's say an intermediate L2, and of course the timestamp manager, for argument's sake, would be in the shared LLC, and that would determine that. Okay, but I'm happy to talk to you about that offline if that didn't answer your question. Go ahead.
Are there issues with timestamp wrapping?
That's a great question. It turns out no. So if you had 64-bit timestamps, then obviously you wouldn't need to wrap around. But it turns out you don't want 64-bit timestamps because of the overheads involved. So if you would like to reduce that to 16 bits, and you have to be careful. And so there's a little bit more that I didn't go over, but it's in the paper, right? So, yeah, great questions. So timestamp compression has to take into account this problem that you just pointed out. So really quickly, I want to give you a sense of why this type of definition of time is more broadly applicable, not just in computer architecture, but in distributed systems. Right? And so let's talk about concurrency control. The notion of sequential consistency translates to what's called serializability in the database world. I mean, not exactly equivalent, but for the purposes of this talk, you can think of them as being equivalent. So what serializability says is simply that these transactions have to be atomic. You can order these transactions in any way, but you can't do that, right? You can't put one of them in another. You can't kind of break the atomicity of these transactions, right? So it's a very clean model. And in fact, transactional programming models are being used in outside of databases as well. In the concurrency control world, people have used logical timestamps. And as I mentioned, multi-version databases came from the database world, obviously. There's a centralized allocator that's usually the bottleneck. And you can order all of our transactions in a particular order, and they don't have to be in the order that they were received. You can choose some arbitrary order, and then you better obey that order in terms of the commit and so on and so forth. But anything that's centralized is usually a scalability bottleneck, and essentially you have loss of performance as you go to more and more cores when you have centralized timestamp allocation. Typically, these algorithms assume you have a synchronized clock, and if you had clock skew, you would have to abort transactions, because what happens is the order that you decided on gets violated kind of at the end of the commit stage, and when that happens, you have to abort. And I'll give you an example of that in a minute. The other problem that we'd like to solve is that it may be the case that a particular order may, in terms of logical timestamps, a particular allocation may result in a smooth execution, but a different order might result in aborts. All right, and so what we'd like to do is kind of do this in a lazy fashion. We'd like to do some reordering, and we'd like to do some time traveling, if you will, even in this context. So here's an example of that. So you have a transaction, and it's T1, and the timestamp that was given was 1, which means that this has to commit. And once it commits, then you can start this transaction because that had timestamp 2, right? So in this case, you do a read here, and you've done a write. The read got the old value. This is happening in, let's say, in physical time, and that's cool. You got no problems here because this read happened before the write, as you can see, right? But if you'd given this timestamp being 2 and this timestamp being 1, you can see that the read is happening here before this write, but it actually has to happen after. It has to get the value that was written by this write because this timestamp was 2. It's a logical time. It just got arbitrarily ordered. So if you chose this, it works in terms of both of them execute. If you chose this, then one of them aborts. And you can kind of create examples where you have a lot of aborts because you just chose these things wrong, right? That's a problem. So the key idea that is additional to the logical timestamp idea in TicToc, which is our algorithm for concurrency control, is rather than acquiring timestamps and determining viability later, is we're just going to use WTS and RTS just like we did before for these tuples corresponding to A and B and so on. So each of those is going to have a WTS and RTS. And we're going to not assign a timestamp to any of these transactions. We're actually going to have these WTS and RTSs for the tuples, the A's and the B's that you've seen. And then much later in the process, we're going to compute a commit timestamp. So we have minimum aborts. I mean, we might have aborts, but we'll try and minimize it. Right? That's the basic idea. And it requires no timestamp allocation because we're going to do dynamic timestamp assignment. So real simple example, and to give you a sense of how TicToc works, you have, as with most concurrency control algorithms, you have a read phase, which is really both a read and a write phase for the tuples. Then you have a validation phase where you determine whether you can complete this transaction and compute a commit timestamp, which is the actual timestamp for the transaction. And then once you've done that, assuming you don't have to abort, you go ahead and do the write. That is, you update the database. All right, that's the classic execution model. We don't change that. You're going to have these tuples with WTS and RTS. Meaning is exactly the same as in the cache coherence protocol. WTS means that you've written that data at that time, and it's valid from WTS to RTS. No changes there. So I'm going to go ahead and read and write the tuples and execute the transaction in the read phase. I'm going to compute the commit timestamp and decide if I need to abort or not, and then I'm going to update the database. So here's a little animation that hopefully makes things clear, kind of the equivalent of my coherence example. So what you see up there is you have two different cores running these two different transactions potentially, as you see on the right. There's load and store associated with this and a commit. Really simple transactions. And there's a database that corresponds to what you see up here. That's the database state, and these are the transaction local states that correspond to these two transactions. So I'm going to go ahead and load a snapshot of tuple A, and I'm going to get some WTS and RTS. It's pretty straightforward. I'm going to try, and I'm going to do the same thing for transaction 2 in perhaps a different core. Now I want to do a store. When I do a store, just like in the Tardis protocol, I have to now create a new version of the data. I'm going to have to take that RTS, WTS to RTS, and I have to jump ahead to RTS plus 1 to create the data. Right? So that's essentially what's happened here with respect to store B. Right? The original thing was 0 to 1. Now it's become, I have to create it at a new version at 2. Right? And then I'm going to now load a snapshot of tuple B, and that's simply a load, so nothing really changes. I go ahead and get the WTS and RTS for B in T2 as well. Right? So now what happens here? I need to compute now the commit timestamp associated with T1 because I've done the read phase for T1. The simple thing that I have to do here is exactly what you should infer from the cache coherence protocol. Whenever I have a write of a tuple, I need my commit timestamp to be greater than, for that write set or for any of those write tuples, I have to be greater than when that tuple expired. I have to be at RTS plus 1. That's what this line shows. And then for the read set, I need that data to be valid. So I need the boundary of WTS and RTS to be within the commit timestamp, right? And that's it. That's the algorithm. So I can compute the commit timestamp over here. And notice that I got a bit of a problem here because I want the commit timestamp to be 2, but the tuple A that I've read expired at 1. But if I could ask for an extension on tuple A, and in this case I will, and if I get that extension, then I've satisfied my property of the RTS and the WTS. Right? So I've decided that the commit timestamp for T1 is in fact timestamp equals 2, right? Now the commit timestamp for T2, once I've done the copy of tuple, I've committed it, so now I'm going to go ahead and copy the tuple from the write set to the database, and I've computed the commit timestamp. Everything is done for transaction T1. Let me go ahead and do the same thing for transaction T2. This is easy. I only had to read a couple of tuples. I can choose the commit timestamp to be 0, or I could choose it to be 1. I go ahead and choose it to be 0. So notice that I've now done this later in physical time, and I've gotten a transaction that has a timestamp that is less than the transaction I just committed, right? The TS equals 2 committed first. So same deal. Physical time is not the same as logical time, right? All right, so I bombarded you with a lot of information. To complete this, it's a similar argument, not exactly the same, but a similar argument that this algorithm would give you serializability, right? And if you're willing to violate serializability and do things like snapshot isolation, the algorithm would have to change, right? And that gives you a little more freedom in terms of parallelism. I will say before I conclude here that we did implement this algorithm. This is just a piece of software. It's a concurrency control algorithm running underneath the database. And what we find is that compared to prior art, in high contention cases, our abort rate is substantially lower, and our throughput is about factor 2 better. Right? Yeah, go ahead.
How do you handle failures?
We don't have a story for failures yet, and that's kind of what's going on out here. At this moment in time, we're assuming a shared memory system which is 100% reliable, and we don't have a story for failures. Let me start with that. So going down to the bottom here and finishing up here, and this is I'm not going to go over show you anymore. This is my last slide. But what we'd like to do is actually solve the problem of parallel logging. So it turns out in order to exploit parallelism and be able to recover when you're exploiting parallelism, you have to be careful that the recovery information that you need, which is basically what you need to put out in log, is something that doesn't destroy your parallelism. Because if you're waiting to write something in a log, and there's complications associated with writing the log first before you commit to the database, et cetera, and so it's a kind of a fascinating set of dependencies associated with including fault tolerance into our scheme. Now, if you're willing to assume that recovery is simply restarting the entire set of transactions and starting over, obviously it's not an issue. But if you want any sort of checkpoint which happens at a fine-grained fashion, then you got to be much smarter about it. All right. That's pretty much it. I hope I gave you a sense of why this is interesting. Going back up here and starting from the top again, it turns out that this notion of WTS and RTS, I feel is something that should be baked into hardware, not just because of cache coherence, but because of other reasons as well. It's because you have annoying things like live lock in atomic synchronization instructions like load reserve and store conditional. When you want to maintain sequential consistency, that rears its ugly head, and there's an elegant way. Perhaps performance doesn't improve, but I would sleep better at night because there'd be a guarantee of correctness associated with ensuring that you have no live lock or deadlock in the use of these atomic synchronization instructions. And so what I'm asking for from computer architects or chip designers is essentially these WTS and RTSs for every data item in the system. Right? If that doesn't happen, and it's not going to happen for a while because chips take a long time to build, et cetera, we're in the mode of using databases and doing things in the database world. And one thing that I didn't talk about that I'd like to briefly mention is because we talked about cache coherence and having many local copies of the data, and we're allowed to do that and we can handle that, in the distributed concurrency control world where I just showed you, or I didn't show you results, I just talked about results in a shared memory system corresponding to corresponding to the concurrency control algorithm. But real database systems are multiple nodes, perhaps far apart with large network latency, and they have sharded databases, so terabytes of data in one and terabytes of data in another, et cetera, et cetera. And it's been really hard for database engineers to use caching. And I mean caching at the level of disk to memory, right? Because you have disks of terabytes and you want it stored in DRAM. So it's been really hard for database engineers to do that because cache coherence is a difficult problem. Basically having data that's consistent is a difficult problem while obeying serializability. These two algorithms, as you can see, they have this underlying basis of physiological time, and they kind of seamlessly integrate, which I don't have time to tell you about. And we only figured this out in gory detail a few weeks ago anyway. But we now have an implementation of distributed TicToc, which is essentially something that runs on a dozen computers with terabytes of disk and does concurrency control across these different computers. Right? All right. Well, hopefully I didn't inundate you, but thank you for your attention. I'm happy to take questions. Yeah.
You didn't say anything about Jefferson's time warp.
Oh, so well, I had these other slides that had anyway. It wasn't Jefferson time warp. Okay. Yeah. I had a slide on the T1000. Right. Yeah.
Is the amount of, or the degree of scalability dependent on like the ratio of the width of the timestamp and the time step that you say the lease time?
There's actually an insight there, and so I'll just kind of reverse it. It turns out that the rate at which timestamps increase is exactly the amount of parallelism. Okay, so it turns out what happens here is that when timestamps don't increase, it means that people are reading data in parallel. And it's a good thing because they're not waiting, that nothing is happening. It's when you have a dependency and potentially because of contention, in the case of the coherence algorithm, or it's actually true even in the concurrency control algorithm, you go ahead and you jump ahead in time because you're trying to avoid dependency. And that's when the timestamps actually increase in size. Okay. So if you kind of look at either of the two algorithms, if you look at the rate at which timestamps increase, that the lower the rate, the more the parallelism there is that's at least being exploited. Not necessarily by any algorithm, but certainly by this one, right? And that's true for, as I mentioned, in all of the different projects that we have going on here. So I would say there's a relationship there, but not quite in the way you said, the way I described it. Right? Did that answer your question, or did I confuse you?
I think confusion is probably closer.
Okay, so could you repeat your question?
I'm thinking, if I have 1,000 processors, or if I have 1,000 cores, or if I have 10,000 cores, do I want that timestamp to be wider? Do I want the step to be bigger or smaller to get that kind of scalability?
So with the rollover trick that we have. We've run simulations of the cache coherence protocol on 1,000 cores with 16-bit timestamps, because they just roll over faster. Now it turns out there is, if you went from 16 to 32, which unfortunately, by the way, has that effect on the L1 cache and increases the size of the L1 cache. But there is a performance impact associated with the rollover because that rollover has, there's some data that needs to be kept synchronized. And so every time you roll over, there's a bit of a penalty associated with that, right? So it's a bit of a trade-off in the sense that you don't want to increase your L1 size by more than 10%, 5%, whatever. But if you're willing to pay the cost and do a 20%, then it'd be fine. In the software world of concurrency control, it's a non-issue because you have these large cache blocks and it's software data anyway. So really, it's much more critical to keep the timestamp small when you're paying hardware costs and SRAM costs for it, right? Right. That make sense?
Partially.
Okay. There was a second part to your question. You said
this step. I'm wondering the step amount.
The step amount, that's a function of the leases. You're right in that if I used a lease of 100 as opposed to 10. Then absolutely that you jump ahead when you do the writes, etc. And that's an issue. So we don't want the leases to be, again, if you had large leases, then you wouldn't have to renew as much. There's a performance implication there. If you use short leases, it's better, even though you might have to renew, because when you actually do the write, you don't invalidate a whole bunch of other data that exists because you jumped ahead so far in time, right? So at some level, this is a quantitative question, right? Yeah.
No need for those lease times to be fixed.
They can totally be adaptive. I mean, I'm fond of saying, especially since I'm hanging out in California, that you can use deep learning to solve that problem, as you can, any problem, any problem, right? So. Yep.
So when is the store visible? Because modern processors have store buffers and all kinds of crazy things.
So I gave you the simplest version of this. So the question is, when does the store commit? And so that's kind of actually related to it is somewhat related to the database world. Where you have to go commit that store into the database.
Then you might have to back abort.
Well, it's possible. It's absolutely.
Okay.
It's possible. But in the cache coherence world, it turns out that you have to be. Let's say you're doing TSO and you have a store buffer, right? Well, I mean, the store buffer also has the WTS and the RTS information in it. It absolutely has to have that, right? And basically, what happens there is, it's possible that if you read from a store and you realize that what is in the store buffer is an expired piece of data, it's possible that your clock has gone ahead in time. This store buffer hasn't fleshed out yet, right? It hasn't been flushed. So this thing is still in there. And it has a WTS and an RTS, and your processor clock is beyond that, right? Then you better not read from that store buffer. You'd be violating. So at that point, what you have to do is you have to flush the store, right? So and then you got to send it out of the system, and then you have to go back to what you were doing.
So this is interlocks that don't exist in existing processors.
That's right. So I will say that it's an invasive modification, which is why I think it's going to take a while to do the kinds of things that the Tardis protocol requires. Right? That doesn't mean we can't build it on FPGAs, and we are, right? But it's an invasive modification. So, yeah.
Maybe stupid, but will WTS and RTS make it into the memory, or does it stay in hardware?
Oh no, it's a great question. It's a great question. So it turns out we don't want to store them in memory. Because there's no way. I mean, where do you put them? You can construct your caches in such a way that you have them, and you can certainly construct the timestamp manager. But I mean, DRAM. What are you going to do with that, right? So it turns out you only have one. We do a sort of a max thingy, where as we are sending things out to memory, we take into account the max RTS of all of these things that are getting dumped into memory, and then when stuff comes back, we have to do something with that, right? So that's a little bit of a detail, and I think I got it mostly right, but I can certainly point you to the paper that tells you exactly what you need to do when you evict things to memory and when you pull things back, all right? But it's roughly what I told you, right? So a good question. I mean, certainly not a stupid question.
Well, you could shove it into, it could be error correcting code, just time correcting code.
Oh, yeah. Well, I mean, there's many things that you could do. In fact, you could use multiple of these. It turns out there's a bit of an issue associated with a single RTS for all of the data that gets dumped out. So if you had more, it would be better. And I guess, well, in the context of fault tolerance or error correction, if you could share those bits, I guess you could save something. Yep.
Cool. Thank you.